All right, trig section 1.3. We're going to need to write at the top of your paper. So, because we're going to need to review a little bit about our trig functions. Sine is our opposite side over a hypotenuse. Cosine is the adjacent side over the hypotenuse. Tangent is the opposite over the adjacent. So let's take a look at example 1. Let's find the sine of theta, the cosine of theta, the tangent of theta. And we want it says the 6 trig function, so we're actually going to need the other 3. What is the reciprocal of the sine called? Does anybody remember? Cosecant. CSC actually stands for cosecant. The C in front is the co, and then the SC is the secant. And then the reciprocal of cosine is just secant, and then the reciprocal of tangent is cotangent. Okay, so let's look at our triangle that we have right here and see if we can figure out the hypotenuse. What can I do to get this hypotenuse? 3 squared plus 4 squared equals c squared. And it is a Pythagorean triple because this will come out to be a 5 when you solve it. So those are all whole numbers, and it's a Pythagorean triple because it's a right triangle. Now, if I'm looking at my top here, my SOHCAHTOA, what is the sine of this theta right here? Where's my opposite side? 4 is my opposite. Where's my hypotenuse? 5, the biggest side, and then the 3 has to be adjacent. So the sine is going to be 4 over 5. And that now gives us the cosecant too, doesn't it? Because we just know that to get the cosecant, we just flip it over. So that's going to be 5 over 4. And the cosine is up here at the top, CAH, adjacent over hypotenuse. So my adjacent side to theta is 3, my hypotenuse is 5. That also gives us the secant. That's just flipped over, you're going to get 5/3. And then the TOA, T-O-A, opposite over adjacent. You're going to get the 4 is the opposite and 3 is the adjacent, 4/3. And then the cotangent of theta is going to be how much? 3/4. You're just going to flip over the tangent, you get 3/4. Now, if you remember from last week, I did mention something about the domain for sine and cosine, meaning how big could sine and cosine actually be? 1 and -1, right? You can't go past those. Basically, you need to have a 0 point something or a negative 0 point something. And it makes sense. You look at these two right here. They're both 0.8 and 0.6. They're both less than 1. Notice the other ones. This is greater than 1. This is greater than 1. This one's greater than 1. This one could be greater than 1. If this one was smaller than 1, then this one would be bigger. So all 4 of these could be greater than 1. These 2 cannot, because the hypotenuse is your denominator, meaning you're going to have the biggest side on the bottom. It's got to be less than 1 whole. So your sine and cosine are always going to be 0 point something or a 1, if that was the case. All right, let's look up at example 2 here. We want to look for the sine, the cosine, and the tangent of 45 degrees. So sine of 45, cosine of 45, and tangent of 45. And they gave us two 45-degree angles and a 90 down here, and they gave us the sides. In every 45, 45, 90, the two legs are equal. You notice how both of these are 1s. They have to be the same. They could both be 4s, they could both be 2s, they could both be 7s, whatever. They have to be equal. And then this hypotenuse is going to be radical 2 times the leg. So this is a 1 radical 2 there. So what is my sine at 45 degrees? What is my opposite side over my hypotenuse? 1 over radical 2. Let's fix that because we can't have a radical 2 on the bottom. So let's multiply the 2 radical 2's. So that's just the same thing as multiplying by 1 whole. But we're getting the radical off the bottom. And you're going to get radical 2 over 2. Now, what do we know about the cosine of 45? It's the same because your two legs were the same. So this one right here can just come down and be radical 2 over 2 as the cosine as well. Sine of 45 and cosine of 45 are equal. Tangent at 45 degrees, opposite side is 1, adjacent side is 1. So 1 over 1, your tangent at 45 is always going to equal 1. You could even test that in your calculator. You could get it in degree mode, you could put in tan of 45 degrees, you'll get out a 1. So that would be the 45 degree angle. Now if you did put in sine of 45 and cosine of 45, you would get 0.707. That's what comes out if you put cosine of 45 or sine of 45. And it's the same answer if you took radical 2 and divided it by 2, you get the 0.707. So that would be your 45 degree angle. All right, let's move to the next one. Okay, let's talk about an equilateral triangle that when you cut it in half makes two 30, 60, 90s. We just covered the 45, 45, 90s, right? Now we want to look at the 30, 60, 90s. So I took this equilateral triangle, and they were all 2s. This is a 2 here, there's a 2 here. This at the bottom was also 2. But when I brought down this altitude, it made 2 1s right here. So I've got an altitude that's going to have 2 short legs that are both 1. Now notice that the short leg is 1 because it's half of my hypotenuse. I took this 2 and cut it in half. Take this 1 and times it by radical 3 and you get the long leg. So 1 times radical 3 would just be 1 radical 3. You don't need the 1 there, but you could put it there. So they want 4 things from us. They want the sine of 60. So let's find the sine of 60 degrees. Here's a 60 degree angle right there. Where's my opposite side? Opposite side is radical 3. Good. Where's my hypotenuse? 2. So I'm going to put radical 3 over 2. Guess what you get when you plug that into your calculator? You get 0.866. That might look familiar from last week. We talked about that on our unit circle. 0.866. Let's find the cosine of 60. On our triangle, the cosine of 60. Cosine is adjacent side. My 1 is my adjacent. Right? What would my hypotenuse be again? 2. So it's a 1 over 2. My cosine of 60 is a half, which is 0.5 if you plug it into the calculator. If you put in cosine of 60 on your calculator, it'll get 0.5. You'll get 1/2, which is 0.5. Now let's move to the 30 degree angle. So we want the sine of 30 degrees. So this time the 30 is up here at the top. Actually, let me put a box around it so it's different. So my 30 degree angle, where's the opposite of that one? The opposite of that is all the way down here at 1. And the hypotenuse is still 2. So my sine of 30 is 1/2, which is 0.5. Notice these 2 problems right there, those 2 answers. They're both a half. So the sine of 30 and the cosine of 60 are the same amount. Notice, what do you notice about 30 and 60 together? They make how much? They make 90, right? That means they're called something special when they add up to 90. Complement, right? They're called complementary angles. If you have 2 complementary angles, the sine of one will equal the cosine of the other. It doesn't have to just be 30, 60. As long as 2 angles add up to 90 degrees, because 90 degrees would be the 2 angles of the acute triangle, the 2 acute angles in the right triangle. Those 2 will equal each other. So that means the sine of 60 and my last one here, the cosine of 30, my cosine of 30 would be my adjacent radical 3 over my hypotenuse 2. That's going to also equal 0.866, which is the same as up there. The sine of 60 and the cosine of 30 are equal because they add up to 90 degrees. They're complements. The sine of one equals the cosine of the other when you're talking about complementary angles. So that's what this means right here. Okay, look at that, and that's a little different notation. Notice how they put 90 minus theta. Because what are they actually looking for when they put 90 minus theta? The complement. They're looking for the complementary angle. So let's just pretend that this theta right here was 10. So the cosine of 10, and what is 90 minus 10? 80. That means the sine of 80 would equal the cosine of 10 because they're complementary angles. Two angles that add up to 90, their sine and their cosine will equal each other. And that's the same thing on this side here, cosine and sine. It's just saying the same thing, but the cosine might be the bigger one or the sine might be the bigger one. This concept also works for tangent. The tangent of 30 is going to equal the cotangent of 60 because those are going to add up to 90 degrees. So tangent and cotangent complements are also the same with tangent and cotangent. And it also works for secant and cosecant. So you can see that complementary angles are important. The sine of one will always equal the cosine of the other. The tangent of one will equal the tangent of the other. The secant of one will equal the cosecant of the other. So those are the cofunctions, and complementary angles are very important there. And again, don't get scared when you see 90 minus theta. All they're talking about is a complementary angle. And I want you to find an angle that will add up to 90 degrees. You just plug in that and you find the complement. It works for tangents, cotangents, it works for secants and cosecants. All right, let's move. Okay, so let's apply now trig identities. There's a little bit you got to write down here, but what's under this box right here is like a little note card, like a little cheat sheet, where you get to use these kind of things on tests and quizzes, and this you'll be able to use this on your notes. This is an important box right here to have these identities down. It will help you solve a lot of different problems. There's three kinds. There's reciprocal identities, and you've already seen most of those already, but I wrote them in a little different format this time. The sine is the reciprocal of the cosecant, and then the cosecant is the reciprocal of the sine. You could do those either way. The cosine is reciprocal of secant. Secant is reciprocal of cosine. Tangent is reciprocal of cotangent. Cotangent is reciprocal of tangent. You should write them in this format, though, because this could come in handy for some of the problems that we're going to do. That would be they're called our reciprocal identities. You have seen them before a little bit, except when I was talking about them earlier, I said the sine was opposite over hypotenuse, so the cosecant was hypotenuse over opposite. We were talking about it in terms of the sides. Now you can just talk about them in terms of themselves. The sine, you can put 1 over cosecant. If it's cosecant, you can put 1 over sine. These are good for substituting. You can take one out and put in the other one. I could take a sine out of a problem right here. I could take this out, and I could put this in its place. That's what we talk about with identities. They're helping us substitute for things. That's why we use them. That's why they're important. So those are the reciprocal identities. There's two quotient identities, two of them, and they're right here. Tangent is equal to sine divided by cosine. Cotangent is equal to cosine divided by sine. We had a homework last week where you were trying to figure out the sign of the 6 trig function of the coordinates on your unit circle. Remember the sine was your y coordinate? Remember the cosine was your x coordinate? The tangent was your y over x, which is what your sine over cosine is, y over x. Cotangent was x over y, would be the cosine over the sine. Because remember, cotangent and tangent are reciprocal. So if tangent is sine over cosine, cotangent's got to be cosine over sine. They're reciprocals of each other. So those are called quotient identities because you're dividing sine and cosine. And there's 3 Pythagorean identities. Pythagorean kind of sounds like what? Pythagorean theorem. So yeah, these are going to be based on the Pythagorean theorem. So your three Pythagorean identities, sine squared plus cosine squared equals 1. Now you could put 1 squared, but what is 1 squared? 1. So you don't really need to put 1 squared because it's already 1. Move it up for a minute, and I'll move it back down in a second. So Pythagorean theorem, a squared plus b squared equals c squared. Sine squared plus cosine squared equals 1 squared, which is just 1. 1 plus tangent squared would equal secant squared. That's an identity. You don't have to prove it. You just have to know it's there in case you need to plug something in. We're going to use one. You're going to use that one today too. And then 1 plus cotangent squared equals cosecant squared. That's another Pythagorean identity. Okay, I'm going to move it back down so we can see the actual example that we're going to need to do here. Okay, here's the example up here. Let theta be an acute angle such that the sine of theta is 0.6. Okay, so the sine is 0.6. Could I take that sine and put 0.6 over 1? Would that be the same thing? 0.6 divided by 1 is still 0.6. So yeah, that would work if I wanted to. Now, they want us to find the cosine and the tangent. They first want us to use the identity. So do you see an identity on this board right over here? An identity that just has sine and cosine in it, and nothing else. Not a reciprocal identity. Not a quotient identity. Right here, you've got this. This has a sine and a cosine in it. It has nothing else in it but a sine and a cosine. So I'm going to take that identity. I'm going to take out sine, and I'm going to put in 0.6. So 0.6 squared. That's what this says. Sine squared, and sine is 0.6. 0.6 squared plus cosine squared equals 1. That's an identity. Yes. X just represents the angle. Or it could be like theta. Sorry. These could be a theta here. So let's do 0.6 squared is 0.36 plus cosine squared equals 1. Let's subtract 0.36. You could actually put 1.00 if you wanted to see the subtraction a little better. You're going to get these to cancel out. You're going to get cosine squared equals 0.64. But I don't want to know what cosine squared is. I just want cosine. How do I get rid of that little square? Square root it. So I'm going to square root both sides. So cosine of x is going to equal how much? 0.8. 0.8 is my cosine. So I used this identity to help me find the cosine. I didn't need to draw a picture. Now I could have. And I'm going to show you the picture down here that would work for this one. But I didn't need to draw the picture. I could simply use this formula, this little identity that will help me find answers to things. Simply plug that in, and you could solve for cosine. Now here's what it would look like in a picture. Remember I told you that the cosine, or that the sine equaled 0.6? So if you look at theta, my opposite side is 0.6. My hypotenuse is 1. So 0.6 over 1 means my sine would be 0.6. If you did a squared plus b squared equals c squared, you would get 0.8 down here for the adjacent. And what is 0.8 divided by 1? 0.8. That's what we got for cosine. 0.8 over 1. So that is a way you can use trig identities. Or I could have went straight to this triangle right here and put 0.6 over 1, put 0.6 over 1, solve for the other side, and got cosine. You could have done it either way. It doesn't matter which way you decide to use. Identities are there to help you. They're like little cheat sheets. You can take one out, substitute things in, and solve for other pieces. So that's how the identities work. All right. Now the rest of them, they go pretty quick here. Last trig identity, and then we've got a couple of calculator ones and a few easy ones at the end. Okay, two ways to solve it. We could use a picture, we could use trig identity. Okay, it says tangent equals 3. So let's look at the picture first. There's your picture. Yes. Oh, did it say it's solved for tangent as well?
Yeah.
Oh, okay. So find the cosine and tangent. So tangent would be 0.6 over 0.8. So down here, tangent would be 0.6 over 0.8. 0.6 over 0.8. Could we reduce that? You could. I'm going to actually multiply them by 10 and put 6 over 8. And then what would I reduce it to? 3/4. So you could actually get 3/4 for the tangent. Now that's using the picture. I could have also plugged in my sine over my cosine, which is 0.6 over 0.8, and I would have got the same answer plugging it into my identity, because it's the same fraction that I got here when I look at my triangle. So that would be the tangent. All right. Sorry about that. Okay, this picture right here is what we would use if the tangent was equal to 3. Now this radical 10, let's pretend like it wasn't there at first. Let's pretend like it was missing. Okay, let's say the radical 10 wasn't there. I just put 3 on 1. Is this a proper triangle where the tangent would equal a 3? My opposite side over my adjacent side. Isn't that what tangent is, TOA, T-O-A? So yeah, 3 over 1. Now how did I get the radical 10? How did I know that this side right here was going to be radical 10? A squared plus b squared equals c squared. And that's how I got this radical 10 right here. So that's how I came up with the triangle. I put in the 3 and the 1 first. Then I did Pythagorean theorem to get the radical 10. Now, what would my cotangent be? Cotangent of theta. You know the tangent equals 3. What do I know about tangent and cotangent? They're reciprocals. So if this is 3 over 1, my cotangent has to be 1/3. Has to be 1/3. You're flipping the tangent over to get the cotangent. Now, what is the secant of theta? What is the secant the reciprocal of? Secant and cosine are reciprocal. Cosine of this angle would be adjacent 1 over the radical 10, right? It would be adjacent over hypotenuse. We want hypotenuse over adjacent. We want the radical 10 over the 1. So secant is going to be radical 10 over 1, which is just radical 10. So there's my cotangent and my secant by using the picture. That means I drew the picture and I found the sides on the triangle. Now let's use the identities. Is there an identity that has tangent and cotangent in it? Yeah, the reciprocal one, right? Where it says tangent equals 1 over cotangent. What could I take out and what could I put in its place? What did they give me? Tangent equals, I'm going to take out tangent, I'm going to put in 3. So 3 equals 1 over cotangent. How do I get the cotangent by itself? Multiply it on both sides. You got to multiply by the denominator, so it's got to be by cotangent. You're going to get 3 times cotangent equals 1, and then divide by 3. Your cotangent is going to be 1/3. Is that what we got up here? Yeah, it is. Now that one you're not going to have to show all that work because you already know that tangent and cotangent are reciprocal. So you would just flip it over. You know tangent's 3, so you would take 3, you'd flip it over, you get 1/3. You wouldn't need to go through all this stuff, but there are other ones that you might need to do that for if there's like radicals involved or stuff like that. So, but this is showing you how to plug something in and solve for it. But let's see how we can go from tangent to secant using the identities. Look at your identities. Is there one that has a tangent and a secant in it? I think it's near the bottom. Doesn't it say 1 plus tangent squared equals secant squared? And we have x's on our chart. You can put thetas in there if you want. It doesn't matter. So let's take out the tangent. Let's put in a 3. So it's going to be 1 plus 3 squared equals secant squared. What is 1 plus 3 squared? 10. You get a 10 here. 10 equals secant squared. Now I don't want secant squared. I just want secant. So square root both sides. You're going to get x is radical 10. No, not x, secant of x. Sorry. Secant of x is radical 10. Yeah. So you can see that that comes out to the same answer we had before. How did I get 1/3 over here? Okay, so I did was I took my adjacent over my opposite, because cotangent is the reciprocal of tangent. Okay, so first I started here. I took out the tangent, I put in a 3. Then I took the cotangent and multiplied it on both sides. So this was cotangent times 3 right here. Then I divided by 3 to cancel those out, and that's why I got my 1/3. All right, last couple are pretty quick ones. We have a calculator page. You get 40 over 60. You get 12 over 3600. This is going to be 5.673 when you put it in your calculator. To get the secant in your calculator, you're going to do 1 divided by cosine of 5.673. 1 divided by cosine of 5.673, because you can't put a secant in just the way it is. So it's 1 divided by cosine 5.673 equals, and you get 1.005. So if you wanted to test that on your calculator, you could test that. Cotangent of 13, you're going to need to do 1 divided by tangent of 13. 1 divided by tangent of 13 equals, you get 4.33. Tangent of 11 degrees, 15 minutes. If you take 15 over 60, you're going to want to find the tangent of 11.25 degrees. That one can go in just as is. Tangent 11.25 equals, you get 0.1989. Cosecant, you're going to need to do 1 divided by sine of 87. 1 divided by sine of 87 degrees. You get 1.001. So those are the calculator ones. You might have a couple of calculator problems where you got to figure out a tangent or a cotangent or a sine or a secant or something like that. Okay, there's a couple left. They're short ones, so let's see if I can get those done really quickly. You're standing 115 feet away. Your picture's right here. From the monument, your angle is 78.3 degrees. You want to find out how tall that is. Which trig function would I use here? I've got opposite side, I've got adjacent side. I've got the O and the A. I got to use TOA, T-O-A. So tangent 78.3 equals x over 115. Do you remember how to solve this equation? Multiply by 115 on both sides. Those cancel out. You get x equals, take 115 times the tangent of 78.3, 555.3. and that's feet. So that's how you apply the trig functions. Again, there's two more that are pretty much this easy, so let's look at them really quick. Hopefully you're not having to write the problems, you just have to do the work with me here. So it says a lighthouse is 200 yards from the bike path along the edge of the lake. Walkway to the lighthouse is 400 yards. Find the acute angle. How do I find this angle? How do I use trig to find an angle? This is opposite, this is hypotenuse. So what function do I need here? What kind of sign? Inverse sign. You need to put sine -1 of 200 over 400. And you need to be in degree mode. So sine -1 of 200 over 400, you should end up with exactly 30 degrees. Do you remember what we got when we put in sine of 30 degrees? If we put in sine of 30, we got 0.5. What is 20 over 400, or 200 over 400 reduced to? A half, which is 0.5. So the sine of a half is going to be 30 degrees. It's always going to come out as 30 degrees there. So this angle right here was a 30-degree angle. And the last one, they all go like I said, these last three go pretty fast. Okay, solving a right triangle. Technically, solving a right triangle means finding all the angles and all the sides. If I wanted to, how would I find this angle right here? What would I have to do to get that angle? You could subtract them from 180, the two that we have, or you could just do 90 minus the 18.4. That would be one way to get the angle, because these two have to add up to 90 because this one already is. Now, we could solve for this bottom side, but we're going to look for the hypotenuse because that's what it tells us. So I'm going to use the 18.4, and this is my opposite. This is my hypotenuse. Could I have used the 71.6? Yeah, but then I would have adjacent over hypotenuse, and I'd have to use cosine. I'd rather use the sine, so I'm going to use the 18.4. So sine of 18.4 equals the opposite 4 over the c. Now, what happens when the c is on the bottom? You got to do one extra step, right? You got to multiply by the c first, get rid of it on the right side, and then you got to divide by the sine of 18.4. So those are going to cancel out. C is going to be 4 divided by the sine of 18.4, and you get 12.67 feet. So that would be your hypotenuse. All right, don't forget your homework over the next 3 days. Get those a little bit done at a time.